part is that the PSO is computationally inexpensive. It doesn't need memory in your computer. Also, it is fast to find out where is the minima or the maxima. So since it is computationally inexpensive and the operators are simple, so computer if we are going to make the program, it is going to be the simple one. And as of now, you might have seen that the PSO code is also available in different programming language such as MATLAB, Python, etc. So let us begin with the PSO. So particle swarm optimization is start with initializing the population randomly, similar to GA. GA stands for genetic algorithm. Just for the sake, I have included so that we can understand how similar and how different it is from GA. Now, when we are saying population, this means rather than we start with the one solution, we are starting with the multiple solutions. However, in the PSO, what we will see that there are certain operators. For example, we are going to update the velocity as well as the position. So these operators are quite simple and different from the GA, which has like crossover and a mutation operators in their algorithm. Now here in PSO, the particle, the solution which we call it, it is referred to as a particle. And in order to understand, there are three distinct features of the PSO. So first is the best fitness of each particle. So when I'm talking about fitness, this means how good a solution is in terms of objective function and satisfying the constraint. So best fitness of the particle, generally we write as a P best I. This means the best solution or fitness achieved so far by particle I. Then comes best fitness of the swarm. Now similar to one particle, there could be say 100 particles. Among 100 particles, which has the best fitness in terms of objective function and satisfying the constraint, which we call, this is generally we refer as G best. And then comes the velocity and position update. So with the help of best fitness of the particle as well as the best fitness of the swarm, velocity get updated, and this updated velocity is going to help us to update the position of each particle. Now let us understand how these positions and the velocities are going to be updated from one iteration to the another iteration. This is the simplest formula which we can see, that x represents the position and v represents the velocity, and I is the ith particle and t stands for the tth iteration. Now if we look at on the right hand side, it says that the position plus the velocity, this means it's nothing but a vector addition. So two vector addition give me the updated vector, which is the updated position of the particle. Now this velocity is also updated in every iteration t, which we can see in equation number 2. Now we can see that this velocity has three components. So first of all, let us understand what are these notations or the parameters which we have referred. As I said, I refers to the ith particle, t refers to the tth generation, and vi0 means what should be the initial velocity. Generally we set it randomly. Now in the first component we can see omega, this is the inertia of the particle. Similarly, if we look at the other two, c1 and c2, these are constant parameters. We call them as a acceleration coefficients. Then this r1 and r2 are the random numbers which are lying between 0 to 1. A computer is generating a random number for us in order to include into this equation. Then we have the parameter PILBT. So this parameter is called the local best. So LB stands for local best, I stand for the ith particle. So ith particle's local best in tth iteration. Similarly, in the third component, we have PGBT, which means this is the global best position of the particle in the tth. So this global best means this is with respect to the swarm where we have many particles. Now, since we have understood that this particular velocity has three components, so what are those components? Let us understand them. Let us begin with the very first component, which is omega v1, which we call it as a momentum part. Why? Because this is the velocity in the iteration t. With the help of this velocity, I am going to find out the velocity in the next iteration, which is t plus 1. So in this case, since we are utilizing the previous velocity for the next velocity, we call it as an inertia component. Now, since this particular velocity is there, we are multiplying with the omega. So not exactly the full component. Some part of the velocity should be used to find out the next velocity, the next iteration velocity. This helps us to prevent particle from drastically changing its direction because it depends on the previous velocity. Then comes the second part, and this second part we call it as a cognitive part. Why cognitive part? Because the current position xit, this is the current position of the particle, and if I'm going to make a difference, so this is the vector difference between the two components and the same particle local best. So this says that how much this particle is far from its local best in last t iteration. So basically it is telling us the memory of the previous best position. So we refer it as a nostalgia, because this particle is always looking towards the local best of its own. Now comes the third, which is called as social part. A social part, it has the component like, again, the vector difference. Here the current position of the particle is we find the difference with respect to the global best, means how far this particle is from the global best of the swarm, and this part we call it as ny. Let us understand the same thing, since I'm keep on repeating that the operators which we are utilizing, they are nothing but the vector operation. So let us understand the same velocity equation in terms of vectors. So this is xit is the current position, and we have three components. This is the velocity component of the previous iteration. This is the local best component ilb, and pgb is the global best component. Now, since we have multiplied omega with this, so this is the this is the final direction for the momentum part. Now, if we are going to have the three vector addition, so you can see that we have this kind of a purple color, which is the momentum part. Then we are adding this red vector, which is the cognitive part. And then finally, we are adding this green vector, which is the social part. And the position of xit is updated with the xit plus 1. So we can say that this particular vector, which is represented as vit plus 1, is the updated velocity with the help of three parts: momentum part, cognitive part, and the social part. So this graphical representation is easy to understand how the velocity is updated in the vector form. Now let us move that how we are going to find the local best of each particle. This can be done with the help of this simple formula, which is given in equation number 3. So what we are doing is, in every iteration, we are looking at whether this new solution, the new position of the particle, the fitness value is better than the local best of the same particle. Here we are assuming that we are solving a minimization problem, so that's why this is smaller than sign we have used it. If the fitness of the new if the fitness of the new position is better than the local best, we are updating the local best for the t plus 1 iteration as the new position. If it is not, then the local best will remain the same. So you will realize that when we are running the local this PSO, the local best may not change for few iteration until we get a better solution than the local best. If we try to find out the global best, so the global best of the swarm can be calculated as, so what we will be doing is, since for every particle we have the local best, among all the local best on the right hand side you can see, among all the local best which has the minimum fitness. The one having a minimum fitness will automatically will become the global best of this. So here we are not taking the current position of the particle. However, we are considering the all local best of the particles, which has the minimum fitness. So this particular thing will become the global best. In our discussion, we are comparing the fitness. However, when we talk about the local best or the global best, we always take a vector, x vector. Now let us understand the PSO algorithm. So first is the flow chart of the PSO. We start with the random initial population in which multiple particles are created randomly. Then we will be assigning the fitness to each particle. Then we will be assigning a fitness to each particle. Then comes the first decision box, which is based on the number of iteration. And suppose t is smaller than t, yes, then we are going to update the local best. And after finding the local best, we will be finding the global best in the iteration t. Then we will be running a loop for all the particles. So suppose we have n particles in a population or a swarm. So we will be taking the particles, all the particle one by one. So first we are going to update the velocity of the particle I. Then we update the position of the particle I. Then we are going to evaluate it and assign the fitness and increasing the counter, and this loops keep on running till the all the particles gets updated. Once it is done, then we will be updating t, which is the number of iteration, and then we will keep on moving in this particular loop till the number of iteration is more than the capital T, and then we terminate the algorithm. So the same algorithm, if we see in terms of algorithmic representation, so we have a solution representation. As of now, we understood as x vector means the real numbered vector. There are certain input to the PSO algorithm such as generation counter, maximum iteration, and few more things we will discuss later. Then we are going to initialize the swarm. So swarm or population is the same. So n particles. Then we are going to evaluate them. So we will be evaluating the objective function, constraint, and assigning the fitness. Then we have a while loop where we will be running this PSO for capital T number of iterations. In step 6, we will be finding the local best of each particle, and among them, we will be finding the global best. Then after finding the global best, we have another for loop for the number of particles, and for every particle, we will be updating the velocity, updating the position, and then finally, we will be finding the fitness, and we are including into the next. So once it is done, the t is increased by 1 and the while loop keep on continue till the termination condition gets satisfied. So let us understand this PSO with the help of one working example. So this is the Rosenbrook function. It's a mathematical problem, and it is a scalable, means if I want to solve for 10 variables, so this Rosenbrook function can help us to write in the 10 variable. For the simplicity, we have taken two variable Rosenbrook function, x1 and x2. The objective function is written. Now you can see that it's not a linear or a quadratic problem, it's a non-linear problem. X1 will be lying between -5 to 5. Similarly, x2 will also be between -5 to 5. Let us look at this graph. So this is x1 versus x2, and the surface which you see is the function, the function which we have drawn. It is a minimization function. Now, if you look at the x1 and x2 plane, these are the contours of this function. Now, looking at this contour, you can see that there are so many local optima, and the global optima is 1, which is lying at 1 and 1, and the objective function at the global minima is 0. Now, since you can see that because of these uneven surface, there are many local optimas, and any of the optimization method or algorithm can stuck to the local optima and may not give the global optima. Fine. In order to understand this, we will start with the initial swarm in which the size is 8 and the number of iteration is t equals to 1. So we will be starting initially. Now for you can see I have used the first column as index I. So you remember that I represents the particle. So the first, second, third, all particles are written. Now initial swarm means the x vector we are generating, and this is we are generating randomly between -5 to +5 for both x1 as well as x2. Currently, we have assumed the initial velocity of all the particles, the initial velocity is 0. So second step, as per our flowchart or algorithmic evaluation, is the population evaluation. So we calculate this objective function as this equation was given earlier. So let us take the solution 1 or a particle 1, and x1 is, so this is the value of x1 and x2. Putting into this, we get the value as 357.154. If I do the same thing for all the particles, so we have 8 particles. So in the last column of the table, you can see the fitness or the objective function of all the particles. Here, we are considering the fitness value same as the function value because we don't have any constraint. So the same value I can use. So the third column, now I'm going to refer it to as a fitness of the particle. Now, since it is the first generation, so we are moving into the another loop which will be running for the all number of particles. In this case, we will be finding the local best of the particle. Now it says that since it is the first generation, local best of the particle is itself. So we don't have to calculate, only we have to assign it. Now see, this is the same table. Now the column number 4 is included. Look at the column number 2, which is xit1, and look at the last column pilbt, which is the local best. Now the x, this is exactly the same. So we have copied. So only in the first iteration we consider this. Otherwise, in the next iteration, I'll show you this velocity. The local best is going to change it. Now let us find out the global best. As per our definition, we are going to take all the local best of n particles, and among them, whichever is the minimum fitness will become the global best. Right. Now look at this table. Now what we are doing is we have these. If you look at the fourth column, this is the local best, and the fitness is given in the third column. Now, if I am going to compare all the fitness, the particle number 4, so the particle number 4 is having the minimum fitness. So this will become the global best for all the particles. Now look at the x1 and x2 value. So the same value is assigned to the last column, which is the global best for all the particles. So that's why the same vector is copied in the last column. Right. Now we are in a position to update the velocity. So this is the formula which has 3 components. So let us assume that omega is 0.75, meaning we are going to take only 0.75 component of the velocity. C1 and C2 we have considered as 1.5 and 2.0. With the help of computer, we generated some random numbers, R1 and R2. As you can see, for every particle, I need 2 random numbers. So for every particle, these random numbers we created with the help of computer. Now, with the help of this data, let us find out the updated velocity. So let us take this particle 1, for which the position is given, initial velocity is 0, local best as of now it is the same, and global best we found out in the previous slide. Putting R1 and R2, if I put into the velocity formula, so since the problem is 2 variable, velocity also has the 2 variables. So the first component of the velocity, so v1 comma 1, this means velocity of the particle 1 and its first component, we are directly including into the formula. So this is the updated velocity. Similarly, I can use the formula for finding out the second component. I get minus 0.822. Now, just one observation, that initially we start with the velocity of the particle at 0, 0. Now, with the help of this velocity formula, Now it is not 0. It has come out to be different, which we are going to use it in the next iteration or generation. Right. The same calculation we can perform for the particle 2. So x2, velocity of the particle 2 is 0, and the local best is given, and the global best, which we have calculated earlier. R1 and R2, and finally we get the first component of the second particle, velocity component, and the second component. Now you can see we get like 0.893 or 2.212. Both of them are non-zero as compared to the previous velocity. If I'm going to follow the same formula for all the particles, you can see that in the column on the right hand, the table on the right hand side, we have 8 particles. For every particle, there are 2 components of the velocity. So vi1 and vi2 are the components. So this using this formula, I can calculate. Now I have marked 2 particular values as red. Here I just wanted to show that you remember that the variables x1 and x2, they are allowed to take any value between -5 to 5. Now this 10 is above 5, minus 5.916. It is even less than -5, which is the allowed value. So I made it red so that you can see that when we are going to calculate the velocity, it can happen, the velocity can go beyond the allowed range of the x1 and x2 variables. Now let us find out the position update. So in the flow chart of a PSO, we started with updating, we started with the random generation of swarm. Then afterwards, we find the fitness. Then we move to the one iteration, find the local best and the global best. Thereafter, the velocity update, and now it's the position update. This position update, we can use it with this formula, which is the vector addition. Now, in the previous slide, you remember this xi, which is the current position, which is the position, this we generated. And in the last slide, we calculated the velocity. Now, in this case, what we will be doing is we are taking the vector sum. So we are adding these 2 vectors. So for example, particle 1, these 2 vectors are added and we get the resultant vector as the updated position of the same particle in iteration number 2. This process, I can do it for all the particles. Now here there is one observation that one thing which I have made it in the kind of orange color is 0, 0. Now here, for the particle 4, the position, the velocity remains the 0. However, for other particles, there are some velocity, some value is there. Now the answer is why it is happening, because you remember that the global best of the particle, global best of the swarm was particle 4. So if you remember this formula where we find out the local best and a global best, so since particle 4 also is the global best, this summation will be, this subtraction will be 0. This is also 0 because the local best of the particle and the current position is the same, and initial velocity was 0, so that's why the updated velocity was 0 in this case. Now, second observation, if I look at the particle's position in the generation number 2, the component, the third, the particle 3 and the second component, which is 5.89, which is beyond than the allowed range as per the question. So we can only have position between -5 to 5. So whenever this is happening, as I have written, x2 should lie between -5 to 5, we will keep this x2 of the solution 3 on the bound. So this means this vector we will be changing at 0.498, and since it is more than the upper bound, so we will keep it on the upper bound, which is 5. Now here you can see I've made it in the orange color so that you can see the change, and rest of the positions remains the same. Now these are the updated position of the particle swarm. Now if I calculate the fitness, so these are the values. Now the interesting part here is, if I look at the initial swarm, this is the first table which I have shown you earlier. It has like all the 8 particles, their current position and their fitness. After one iteration, these are the these are the updated position, these are the fitness. Now if I compare the fitness in just one iteration, you can see one of the solution has a better fitness than the best, which was 167 in the initial swarm. This observation tells us that if we keep on running the PSO iteration by iteration, fitness of one of the particles will keep on reducing, and after some time, the algorithm PSO may converge to the optimal solution. Right. So now in this case, we are going to increase the generation counter by 1. So we have t equals to t plus 1 equal to 2. Just for the sake of completeness, I will be showing you the calculation for the second generation. Why? Because in the previous generation, the velocity was 0. Initial velocity was 0. Now this velocity has been updated. Now you can see there are some changes in the calculation. So we'll see the velocity update now. So we have this formula, and omega C1 and C2 values are the same. We generated the random number with the help of computer, R1 and R2 for each of the particle. So let us take the particle 1. Now you can see this is the updated position. This is the velocity after iteration number 1, R1 and R2, and this will help us to calculate what will be the updated position. Now, in order to find out the velocity, we should know what is the local best, as well as we should know what is the global best. Then only I can find out the velocity of the particle. Now, since what we have seen, the particle 1 in the initial swarm, the fitness value was 357, and after one iteration, it will become 399, meaning that the particle, when it moved from its initial position to the next position, the fitness was bad. So in this case, as per our definition, the local best of the particle will remain the same as the previous one because it was the better position. So the local best of the particle will remain the same as the previous one. So that's why this number 2.212 and 3.009, it's the same as we have shown in the initial swarm. Now, similarly, we have to find out the local best of all the particles, as well as then with the help of that, we can find the global best. So let us do this exercise. This in this particular table, I'm going to show you for each of the particle. So particle 1, the column 2 will be the the fitness value of the initial swarm, fitness value of the updated position. Now, if I look at both of them, so I can understand that 357 is smaller than 399. So the local best position will be corresponding to the previous position. If I look at this particle 2, comparing the fitness, I can see that the updated position is better than the previous one, and therefore the local best of the particle 2 is updated. And if I follow this, comparing the current fitness and the previous fitness, we can see that the current fitness for 3, 4, 5, 6, 7, and 8, all the particles that is better, and therefore the local best of these particles are updated. Now, similarly, if I have to find out the global best, so as per the definition, global best is the one which is having the minimum fitness. So if I look at the third column, which is corresponding to, or if I look at the green values, the values under the green, because these are the local best of particle 1 to 8, among them, the minimum is 153, which is corresponding to the solution number 7. And this will become the global best of the swarm for the PSO. So we can say that the global best in iteration number 2 is the same X value which is written for the particle number 7. Using excuse me. So using the local best of each of the particle, global best of the swarm, and the formula which we have used in this previous slide. So now I have the value of each and every component in this formula. I can find out the updated velocity of each particle. So this means the velocity in the third iteration, the first component and the second component for all the particles are written here. For updating the position, we again using this formula where we are adding the velocity and the position together. So this is the position in the second iteration. This is the updated velocity for the third iteration. If we perform the vector sum, quite straightforward, we can find out the updated position for the third iteration. Now there are certain observations. So I have marked some numbers in the red. If I look at the particle number 3, the second component 9.825, it is more than 5. Similarly, the second component of particle 6 is also more than 5. Now looking at the particle number 8, the first component is more than 5, which is the bounds minus 5 to 5 as per the question. Since they are going out of the bound, so we are putting the bound. So these values, we are again taking them to the value of 5. Now here you can see this is the fitness of the particle after second iteration. In the blue color, you can see that we have changed the say x2 part of particle 3, x2 part of particle 6. We put it as a 5 because that is the allowed value. Similarly, for the particle 8, x1 is also 5 because that is the allowed value. Based on that, if we calculate the fitness, the observation is that the solution 5 having a fitness of 13. Now let us compare the same fitness for the first generation. So again, in the initial fitness to first generation, there was an improvement. And the best fitness was 153. After third iteration, you can see that the fitness has reduced to 13.22. And when I discuss this particular problem, the best fitness is 0. Best fitness is 0. It means that you can see that from initial swarm to the second generation to the third generation, the fitness of the particles fitness is reducing, and if we keep on running, the PSO is going to converge to the optimal solution. Right. So let us see the same thing and as a graphical example. This was the initial swarm. So I have taken the same example, same solution, so that we can understand graphically what is happening. So this is the optimum solution which I am representing with the help of this red dot. And these blue dots are the solutions in the initial swarm, 8 solutions which we have considered. Now you remember that we are going to find out the local best. So they themselves are the local best in the iteration number 1, and the global best to the one which having the best fitness among all the local best. So this is represented by this pink color. Then the velocity component. So if we combine all the 3 components of the velocity, the resultant velocity I am showing you with the help of these arrows. So how the solutions are moving. So for example, if I take the solution number 2, this blue point is going to move to this particular orange point with the help of this velocity component, which is shown as an arrow. Similarly, for all the particles are shown. Then this will give me the updated position. So these black dots are the updated position. Now the observation is that initially the particles were distributed. Now these black dots are trying to converge to the optimal solution. In the next iteration, as I have showed the calculation, the hand calculation, again we will be showing the velocity component. So if you look at, say for example, this black dot, the black dot having this green arrow and this is the orange. So this is the way the position is going to be updated. The updated positions are shown in this pink colors, and the red is the optimum solution. Now what you can observe that on the right hand side, this was the initial swarm where the solutions were distributed randomly. After running the PSO for 1 and 2 iteration, these are the updated positions of the particles. Now if I look at them, these particles are trying to move towards the optimum, and in few iteration we can expect the solutions or the particles are going to converge to the minimum solution. Right. Let us come to the simulation part. I'll take the first question as the same Rosenbrook function. Earlier, I told you that this Rosenbrook function is the scalable problem. So from 1 to n variable I can consider, and this is the formula. And all the variables should lie between -5 to 5. And this is the same plot which we have shown. And the optima will always be lying on 1, 1, 1. And the function value should be 0 at the optimum solution. Let us solve this problem for two number of variable. We are going to take 40 swarm size. Number of iteration to terminate PSO is 200. C1 and C2 we have taken 1.5. The inertia value omega, we have used this equation, straight line equation, which depends on the current iteration t and the maximum value t. So this means initially it has a small component adding to the W max, and in later this is bigger, so W is going to be 0 in the final iteration. And initial velocity of each particle is 0. On the right hand side, you can see the x1 and x2 plane where the contours are shown. The blue dots are the random particles distributed, 40 random particles. And the red dot is the optimum solution for us. So let us see the simulation. I hope you can see how these blue dots are moving. So these blue dots are the updated position iteration by iteration or generation by generation. On the top, you can see the generation counter is increasing, and these blue dots are keep on changing their updated position. And sometimes you will see that some blue positions are quite close to the optima. And since these positions are keep on updating, so that's why these blue dots are moving. Now let us look at the progress. Progress means we will be looking at the x-axis as the generation, y-axis as the best fitness we have achieved so far. So we can see, let this iteration finish, then we can have more understanding. So let it finish for 200 generations. So you can see we started somewhere 6.5, it get reduced in few iterations. It is quite close to 0. And like you can see small change near 30 iteration, somewhere close to 70 iteration. And this particular line is going close to 0. This means the best fitness is close to 0 means we have already find out one solution which is close to the minima. And as per this particular graph, we can see that the PSO is able to solve the Rosenbrook problem, which is very difficult to solve because it has so many local optimas. Right. The second problem which I'm going to take is the Hamel-Blau function. Hamel-Blau function itself is the two variable problem. And in this case also both the variables x1 and x2 should lie between -5 to +5. This problem is called as a multimodal function because it has 4 minima. Now you can see these small 4 circle, all of them is the optima, and this is the surface of the function. Now these 4 optimas are written as 3 by 2, 3, 2, -2.8, 3.15, -3.7, -3.2, and similarly 3.5 and -1.8. And the function value is the 0 at all the points. In order to solve this, we are taking the same same value of the parameters, such as swarm size is 40, number of generation is 200, C1, C2 is 1.5. We are again using this linear equation for finding the omega value, which is based on the current iteration versus maximum number of iteration, and the initial velocity is 0. On the right hand side, we can see these are the blue dots, which is the initial particles which are generated randomly in x1 and x2 plane, and these are the contours. So these small 4 circles, these are the optimas. Let us see how PSO is going to solve this particular problem. Now you can see these are the current positions which are keep on updating generation by generation. So x1, x2, and on the top generations are shown. Now you can see that these particles have found at least one minima of this particular problem, because red dot is not visible. So these blue dots are already converged. So here you can see that this is all the blue dots are, they have at least find out one minima for the given problem. Let us see the progress now. It is started with 3.5. In less than 5 iteration, it is close. It is almost zero. And since we have already achieved the optima, we cannot expect that this particular line will go further down, because the minima is already found within the 10 generation of the PSO. Right. Let us move to the third problem, which is the Rastrigin problem, and one of the most difficult problems in the area of optimization. If, say, suppose you are working in any of the method or algorithm, and this method is able to solve Rastrigin function, so you can consider that method is a good method, because as you can see, this Rastrigin method, if you look at the plot, this is only for two variable x1 and x2. There are so many ups and downs in the surface. Ups and downs means this is going to create lot of local minimas. Now, if I look at x1 and x2 plane, these small circle, these are the contours. Everyone is like a local minima, and the global minima is lying at the origin, and the function value is 0. Similar to the Rastrigin Rosenbrock function, this Rastrigin is also the this is a scalable problem where I can choose how many variable I want to solve it. And it is a nonlinear problem. As you can see, the formulation itself involve cost term, and with respect to the xi. So it is going to be the nonlinear problem. Let us solve this problem for two number of variables. The rest of the parameter remain the same, as sum size is 40, number of generation is 200, C1, C2 value, omega is again like a straight line, it is going to reduce from the maximum to the minimum value, and the initial velocity is 0. On the right hand side, as we can see the contours on x1 and x2 plane. Blue dots are the initial particles which are randomly distributed. Red dot at the middle is the optimum solution for the given problem. So let us see how the PSO is working. Now we can see that again these the particles are updated in every iteration. They started coming closer to the global minima, which is the red dot, and some of the blue particles have already converged to the global minima. So if we can see that although the problem is so difficult, where the problem has so many local optimas, PSO is able to solve this particular problem. Let us see the progress. Again, generation versus fitness. How you can see this is the fitness is keep on reducing. Just before 50, the PSO reached to the close to the minimum, and then maybe after a few iteration, it will be there is a small change just before 110, and now we have reached to the 0 value. This means we have identified the minima of the Rastrigin problem, which is quite difficult to solve. Let me take the last problem here. This is the Akhilesh problem, in which we are minimizing the function, and again it has like exponential component, cost component. So this problem is going to be the nonlinear problem. And in this case, x1 and x2 are lying between -5 to +5, and you can see the surface. So for the given problem, you can see there are ups and downs in the surface, and because of that, if we look at the x1 and x2 plane, these are the contours of the problem, and the minima, there are so many local minima for the given problem. The exact or the optimal solution or the minima is lying at the origin, and the function value is 0. In order to solve this particular problem, the parameter, the value of the parameters for PSO will remain the same as we have taken earlier. So n equal to 40, t equals to 200, c1, c2 is 1.5, omega is varying with respect to this straight line equation, and v velocity, initial velocity is 0. On the right hand side, we have x1 and x2. Again, blue dots represent the random initial particles. Red dot is the optima for the given problem. And these circles which you can see, these are nothing but the local optima, and the global is 1. Let us see the simulation of the PSO in order to solve this problem. Now you can see in the very beginning itself, the blue dots have already converged to the optimum solution for this PSO. And then since it has converged, then all the particles will try to come to the minimum, this global optima. Okay, let me see the progress generation versus the best fitness. We can see that around 40, 50, we are very close. And just after 50, or again after 70, we have reached to the minima for the given problem. So, although this particular problem has so many local minimas, the PSO is able to solve such kind of difficult problems, uh, with, uh, such types of difficult problems in a quite easy way. I have come to the closer of this session now. So what we have discussed in this session is we have discussed about the distinct feature of the PSO, in which what is global best, local best, how we are going to update the velocity and positions. We understood it. With the help of these parameters, we have used those vector equations in order to update the velocity. So three components were discussed. And using that updated velocity, we are going to we updated the position of the particle. We understood this PSO with the help of flowchart and the algorithmic representation of a PSO, so that how it is working, how many loops are there, where the position will be updated, or the local best and global best, we understood through the flowchart. We took the working principle of the PSO. We took the example of this Rosenbrook function, two variable, and then we saw how it started, and with iteration number 1 to 2 to 3, the fitness was reducing with the help of velocity update, that when it was added to the position update. Graphical example we have shown, that was the representation. Finally, simulations of the PSO was shown, and the four problems were solved. Those were Rosenbrook, Rastergen, Hamel-Blau, and Eckley function. Now, what here we can see that all the functions are difficult to solve, and they somehow represent the scenario which we find when we are solving the real world problems, because the real world problems can have so many local optimas, equation can be highly nonlinear. Instead of one minima, there could be multiple minima, which we call it as a multimodal functions, and so on. And the performance of the PSO on these problems, we can see that PSO was able to solve the problem quite efficiently within the allowed number of iteration. Just for the information, every year there is a course on NPTEL on evolutionary computation for single and multi-objective optimization. So I prepared this particular course for NPTEL, and every probably it is starting every January of the year. This course is floated by the NPTEL on SWAM platform. So if anyone is interested to know further about the PSO and other evolutionary algorithms for single and multi-objective, they can always register. However, the YouTube channel, the YouTube videos are already available. You can always Google it. You can see those videos because it is freely available. So with this, I conclude this session. If there are any questions, any queries, I'm ready to answer all those queries.
Thank you so much, sir, uh, for this very nice presentation and very elaborately discussing the topic of particle swarm optimization. I would request the participants if they are having any query. We are having one query, sir. If you can see this one, sir, at page number 1, how to work velocity and what is the role of C1 and C2.
Okay,
Sir,
slide number 8.
8, sir.
Right. Okay, so the question is how to work velocity. What are the role? Okay, fine. Now, what you can see that if I look at this component C1 and C2, these are the constant parameters, and we call it them as a acceleration coefficient. If I am going to take the small value or a large value, that is going to affect my final velocity. Say suppose if I take the small value of C1, this means I will be giving more emphasis of the current position with respect to the uh, uh, local best. I will be giving less priority or less importance to the current position with respect to the local, and we are saying that PSO should work based on the global best if C2 value is more than C1 value. If I take otherwise, this means I'm C1 is more than C2. It means we are more focusing on the current position with respect to the local best, with respect to the rather than the global best. Now both have their own significance. This means that if I'm giving more importance to the local best, then these particles, the velocity will be decided or will be updated in such a way that it will be keep on revolving around the local best. If I am giving more importance to the global best by increasing the value of a C2, this means means all the particles will be revolving or moving around the global best, so that this may help us to convergence. So the first part will help me to explore the search space if I take more C1 value. The second part will help me to concentrate on the areas where we can expect there will be, minima. The more larger value of a C2 will be helpful. So that is the significance of C1 and a C2 here on the velocity term. Now, if I look at R1 and R2, R1 and R2, we are keeping it random. Why? Because this evolutionary algorithms, we want them, they should be stochastic algorithm. Even though we have fixed C1 and C2, some numbers, we want some randomness in calculating this velocity with respect to the local best and the global best. Because if we don't involve this randomness, it may happen that the algorithm may converge to say some artificial local minima or some local minima rather than the global. So this randomness help the algorithm to come out from those local zones and try to explore and find out the global. So that is the role of R1 and R2. This means it is going to help us to incorporate stochasticity into the evolutionary algorithm, or we can say PSO. Yeah, I hope this is. If you have any other question on that, let me know.
I hope the query is clear, Mr. Hajaruddin. So I once again thank you, sir, for this wonderful
Sir,
presentation.
sir, I have one more question. In the velocity equation, how to relate the particle swarm?
Can you repeat again your question?
Oh, last question is left. In this velocity equation, how to relate with particle swarm?
In this velocity equation, how to relate with the particle swarm? Okay.
Yes, sir.
Okay. So particle swarm, how we understand particle swarm? We understand the particle swarm in such a way that there are group of particles, and these group of particles are moving from first position to second position. How they can move? Because they are moving with a certain velocity. So this velocity factor is coming. So this velocity component, when I'm going to add the current position, the new position will be updated, and that new position may be closer to the optima. So since this velocity component will be telling us in which direction and how far I should go, so that's why this equation has an importance in finding the new position, right? That was your question or something else?
Yes, sir. Thank you, sir.
Yeah. Okay.
Yes, sir. Thank you, sir.
Thank you. Yeah, is there any other question?
Sir, on the slide number seven.
Yeah.
So this is the equation one is the position vector, right?
Come again?
The equation number one, sir.
Yeah.
So this is simple vector addition or something else? Because we are adding position and this velocity together in this equation.
Exactly. So as I told you that this is nothing but a vector addition. And in this slide number 9, now you look at this. What I'm showing is like we have the current position X. We have 3 other components related to velocity, local best, and the global best. By adding their corresponding parts, you can see that this is nothing but the vector addition, and finally we get the updated position.
Thank you.
Okay, sir. Thank you. I hope there's no more question. And sir, your email ID is already present in the site. And participants have any query, maybe they will be allowed to send the question. If they
Right.
have any. Okay. Thank you, sir. So we are stopping this session at this point. Thank you once again, sir, for enlightening us with your presentation.
Yeah. Yeah. Thank you very much. Thank you all of you for your patience. I know that the optimization now is an integral part of all of your calculations, and even in your personal life as well. So sometimes these algorithms are really helpful to deal with the problem, solve the problem, come up with the optimum solution. So I hope particle swarm optimization as well as some other optimization techniques will help you, in doing your research as well as involving, these algorithms in your real world problems to take the final call or take the final solution. So with this, all the best to everyone, and thank you to the organizers for calling me for this session. Thank you very much.
Thank you, sir.